So to draw the line angle structure of 2-chloro, 3-ethyl, 2-methylpentane, the first thing we do is identify the parent. So that's the easy part. Even though this name is long and it seems like it might be complicated, just start with what you know. And what you know is the parent. So the parent is pentane. That means it's 5 carbons. So just start by drawing those 5 carbons and then number them. And the carbon number. So there are our 5 carbons for pentane, and then we're just going to go ahead and add the substituents. So we have a chlorine on carbon 2. On carbon 3 we have an ethyl group, so remember that's a 2-carbon chunk that is attached as a substituent. And then on carbon 2 we actually have a methyl group, so we have 2 substituents there. There you go. So for the second problem, we're going to take the same approach, and that is, we're not going to worry about all this other stuff for this really long and seemingly complicated name. We're just going to start with what we know. So we know that the parent is nonane. It's an alkane with 9 carbons. So we're just going to draw the parent chain and count our carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we're going to number them. Same thing that we did last time. So that way we know where everything is going. Okay, so we're just going to walk through this. So on carbon 5 we have something that's a little bit more complicated. We're going to come back to that. So let's just skip ahead. We have 4 methyl groups, tetramethyl, and we have a methyl group on carbon 2, on carbon 3, and 2 methyl groups on carbon 7. So we're just going to draw those. So there's 2, 3, 7, 7. And then we're going to come back to what is attached at carbon 5. So at carbon 5 we have a branched branch. And so we have to use a secondary numbering scheme. And so we're going to just look inside the parentheses. So the branch that we have attached is a propyl group. Okay, so that's 3 carbons. So on carbon 5, we have this hydrocarbon chunk that has 3 carbons, and we're going to go ahead and number that. So that way we know where the branches of the branch happen to fall. So there's our propyl group. We have 3 carbons. On carbon 2 of the branch and on carbon 2 of the branch, we have methyl groups. So we have a methyl and a methyl. There you go. So for this problem, the first thing I want to point out, because I ran out of room here, is that when you write the name, there shouldn't be a space between the last substituent and the parent. And so if I had more room, this would all be one word, so to speak, isopropyl dodecane. So I just want to make that comment so you don't think that there's supposed to be a space there. We're going to follow along with what we've done previously, and that is start with what we know, which is the parent chain. So remember that decane is 10, dodecane means 12. So we're going to draw a parent chain with 12 carbons. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm always 1 carbon off. 12. And, following along with what we've done previously, we're going to number them. And then it makes adding the substituents pretty straightforward because the carbons are already numbered, and as long as you know what those substituents look like, you just have to tack them on. Alright, so let's start at the beginning. There's a bromine on carbon 9. There's an ethyl group, remember that's a 2-carbon chunk, on carbon 3. There's an iodine group on carbon 2. And then on carbon 5, there's an isopropyl. Remember that isopropyl is IUPAC accepted, and so you can just call it isopropyl, and it's alphabetized according to the I, or the name could have used the branch of the branch like we did in the last problem, and this piece could have been named 1-methyl ethyl. in terms of a branched alkyl chain. But we're going to go along with what the name was that was given, and there's the structure. So for the last problem, we're going to follow the same approach, only notice that this time, again, in the interest of board space, running out of room, that should be all one word, but our parent is not hexane, but it is cyclohexane. So we're going to start by drawing the parent piece. There's our cyclohexane. And then we're just going to do the same thing that we've done previously. Now in this case, because we are attaching the substituents where they need to go, we can number the cyclohexane starting with any carbon and just going around the ring. It doesn't really matter if I started the one here or the one here. We just need to make sure that those carbons are numbered all in a sequence. And then we apply the same steps. So on carbon 2, there's a methyl group. On carbon 4, there's one of these branched chunks. We'll come back to that just like we did in the previous problem. On carbon 1, there's a propyl group, a 3-carbon chunk. And then coming back to carbon 4, we have a 2-methylpropyl. So we have this 3-carbon chunk that has its own branching, so we need to number that piece. So there's our 3 carbons. There are our 3 carbons for propyl, and then on carbon 2 of that alkyl chain, there's a methyl. So when going from structure to name, the most important thing is you have to find the parent chain. And the parent chain could be what seems like sort of the straight across horizontal chain that might be the obvious choice, or it might not be. And so the trick here, when you start with a structure, is you must identify the longest chain. And so sometimes that means starting from what seems to be the end of a substituent and going through the chain. Sometimes it's starting at what seems to be the beginning. Sometimes it's starting at what seems to be the end. You just have to find all of those paths, and you have to identify the longest path. In addition to that, there are times where you might have 2 paths that are the longest path. So then the question is, well then how do you distinguish? You distinguish which path is actually the parent by the one that has the most number, the greatest number of substituents. So we'll run into a situation like that, but let's just start with what we're given. We don't know where we're going to go, and we're going to figure out the longest path. So we're going to start with what seems to be obvious, and we're just going to start counting carbons. So I'm going to write the carbon numbers here, and eventually I will use the magic of the whiteboard and I'll erase them so that way the structure is a little bit cleaner. But let's just start with all of our options for now. So what seems to be going from beginning to end gives us a chain of 6 carbons. Okay? If we go in this direction, there's a substituent at carbon 3. So remember that in addition to dealing with 2 paths that have the longest chain, and wanting to identify the greater number of substituents, the other thing that you have to worry about is that the substituent is attached to the carbon number that is lower, if possible. So, to illustrate that, if we number that same chain backwards, notice that the substituent for the green numbering is on carbon 3, but for the blue numbering it's on carbon 4. So if we were to choose between these 2 numberings, we would choose the green one. But that might not still be the longest path. So we need to see what happens if we go down this path. We might actually end up with a greater number of carbons. So if we start here, we would have 1, 2, 3, 4, 5, 6. Okay, there's another 6. So we'll number that like this. But then it's looking like if we start to number it from the other end and go this way, we're actually going to have a greater number of carbons. So 1, 2, 3, 4, getting kind of complicated, 5, 6, 7. So notice that the numbering with the black set of numbers is giving us a 7 carbon chain, whereas so far everything else was a 6 carbon chain. So let me go ahead and erase all of those that gave us 6, because we know that's not going to be the case. But the other thing we have to check is the direction. So in the numbering that we've just used, we started here and went down that path. So remember that now the deciding factor is the greatest number of substituents or the substituent on the lower number. So going with this path written in black, the substituent is at carbon 4. If we start the numbering in this direction, the opposite direction, the substituent is at carbon 4. So in this case it doesn't matter. We can use whichever direction of the numbering we want. It ends up being the same. Okay? It's not a bad idea when you're first learning how to do these to circle the parent chain. And that way you see the substituents literally sticking out from the parent chain, and you're less likely to forget one when you go to name the entire molecule. Okay, so we can go with either numbering. So we'll just go with the numbering in black. And so the parent chain has 7 carbons, so we know that that's heptane. And there is a substituent at carbon 4, and that's all we have. So the substituent at carbon 4 is an ethyl group. And so the name becomes 4-ethyl. Remember that between the last substituent or the final substituent and the parent, there's no space, no dash, no comma, nothing. So it's 4-ethyl, all one word, 4-ethyl heptane. So for this one, the first step is the same as what we did with the previous problem, and that is we have to identify the longest carbon chain. So it makes sense that we could start our numbering just across from what seems to be beginning to end, and then we'll start to address if that's actually the longest chain and or the proper chain as we check all of these other directions. So if we go in this direction, we have 8 carbons in a row, and we have substituents on carbon 3, 6, we have substituents on carbons, So for this numbering, with 8 carbons in a row, we have substituents going in this direction on carbon 3 and carbon 6. If we were to number that same chain in the other direction, those substituents are on 3 and 6. So we either have them on 3 and 6 or 3 and 6. So at this moment it seems like they are essentially equal, but we'll get to whether that is actually the case or not in a little bit. We might need to try this path. So if we started up here, we would actually have 1, 2, 3, 4, 5, 6, 7, 8. So we also have 8 in a row. So we should number that one to see if the substituents are on lower numbered carbons. In this case, we actually have a substituent on 2. We have 1 on 2, 1 on 3, and 1 on 6. So for this numbering, not only do we have substituents on lower carbon numbers because they start at carbon 2, we actually have substituents on 3 carbons. Right? So if we look at the green, I should have written this down earlier, we have a substituent on carbon 3 and carbon 6. That's all we have. For the blue, in the opposite direction, we have 3 and 6. And yes, I recognize that whatever this carbon number is here, we actually have 2 substituents, but for the moment we're just looking at which carbon numbers have things attached. And so for the red path, we actually have substituents on a greater number of carbons. So that is going to be the path. Now, we should really check the opposite direction to see if that changes the lower numbering. So if we were to number in the opposite direction, 1, 2, 3, our first substituent appears at carbon 3. So in fact, the direction that we've already written turns out to be the correct one. So we need to now identify what those substituents are. And so let's get rid of the numbering that we're not using. And again, when you're first learning, actually not when you're first learning at all, it's a good idea to circle the parent chain, because especially on an exam, it is easy to miss something. Okay, so we're going to circle the parent chain, and then we're going to identify what the substituents are. We've already identified at which carbon numbers they appear, but now we need to see what exactly we have. So at carbon 2, we have a methyl group, a 1-carbon chunk. At carbon 3, we have a 2-carbon chunk, an ethyl group. So I'm just going to take these notes right here. Over here at carbon 6, we have another methyl group, but we also have a chloro group. So the next step, or the last step, is that we have to assemble these in alphabetical order. And in this case, we actually have methyl groups appearing at 2 locations. So we have to indicate the numbers of both of those locations, and because there are 2 of them, we have to use the prefix di in front of them. And remember that the prefix di doesn't count in the alphabetizing. So we've got alphabetizing with the M for the methyl, the E for the ethyl, and the C for the chloro. So the chloro will be first as we assemble the name. The ethyl will be second, and the dimethyl, those 2 methyl groups that we sort of lump together as a dimethyl, will be the third substituent, and then that runs into the parent chain, 8 carbons, which will be octane. Okay? So the name is 6-chloro, the ethyl is second, 3-ethyl, and then it's 2,6 dimethyl, and then that runs right into the parent chain, which is octane. So this problem has a slightly different feature, and that is that it's got a ring attached. And so what we have to decide is whether the ring is the parent or if the ring is a substituent. And the general rule is you count the number of carbons in the straight chain part of the hydrocarbon and compare that to the number of carbons in the ring. And whichever piece has the greater number of carbons, that will be the parent. So you can see here we have a 5-membered ring, a cyclopentane, and we clearly have more than 5 carbons with the straight chain part. So that tells us that this is going to be a substituent and the parent is going to be along this path. Okay, so if we start numbering, again, just pick a direction and see how many carbons you end up with. We have 6 in a row. If we were to also bend this around and end that here, it would still be 6 in a row. Except for, I think it's pretty clear from this example, if instead of taking that carbon as number 6, we continue up what seems to be a substituent, then we end up with 7 carbons in a row. So there isn't a lot of branching here. It's not that complicated. Our parent is 7 carbons in a row. So we've numbered in this direction, but we also need to check the opposite direction. We know that because we're not going on different paths, it's just the same path in opposite directions, that the number of substituents will be the same, but we just need to check the carbon numbers to see which direction gives us the lower set of numbers. So if we look at the blue direction, we have a substituent at carbon 2, carbon 5, and another one at carbon 5. And if we look at the green direction, we have substituent at carbon 3, or substituents at carbon 3 and at carbon 6. So it turns out that for this case, the blue path is the parent chain and the direction of the numbering. The next thing we have to do is name the substituents, and we'll go ahead and also give them their carbon number or locant so we know where they are. So we've got a cyclopentyl on carbon 2, and on carbon, let's see, we're looking at the blue chain. Blue pen is running out. On carbon 5, we have 2 methyl groups. So remember that you have to identify the location of each methyl group. So even though it seems redundant, you have to indicate one of the methyl groups is on 5 and the other one is on 5. And then just like the last example, when we had 2 of them, we have to add that prefix di for dimethyl. But in this case, it turns out that they happen to be on the same carbon. We then, when we go to assemble the name, we still have to deal with the alphabetizing. So the di doesn't count. The alphabetizing goes by the methyl. But over here with the cyclopentyl, the cyclo part counts. So the cyclopentyl substituent goes first in the name, the dimethyl goes second in the name, and then that runs right into the parent chain, which is heptane. So the name, when it's assembled, if we had functioning pens, that would be awesome. 2-cyclopentyl dash 5,5 dimethyl, all one word, heptane. So for this molecule, we don't have, very clearly, a large number of substituents, but we do need to be careful in identifying and numbering the chain. So let's start with what seems to be obvious. Just writing the numbers all the way across. So we have 10 carbons in a row. If we were to go this path, but then go into what seems to be the substituent, we have 6, 7, 8, 9. Okay, so that's not going to work. So that's all we have. Those are the only possibilities, is we take this carbon chain up into the substituent, or we just look at it straight across. We should actually double check though from this direction going this path. So 1, 2, 3, 4, 5, 6, 7, 8. So clearly this is our parent chain. But the other thing we need to identify is this one substituent right now with the blue numbering is on carbon 6. We have to see if we number in the opposite direction, if we end up with a lower carbon number. And in fact, when we number in the opposite direction, the green numbering gives us the substituent at carbon 5, so it's the green numbering that we're going to use. The second thing that we notice is we have a branched substituent. So we have to identify the secondary numbering. So the numbering of the substituent, remember the point of attachment is carbon 1 of the alkyl group, or of the substituent. So 1, 2, 3 is the numbering for our substituent, and then we have stuff attached. So for the substituent itself, we have a bromine or a bromo on carbon 1, and we have a methyl on carbon 2. When we assemble the name of the substituent, that is going to go in parentheses, but identified by its carbon number attachment on the parent. Okay? So on carbon 5, we have this stuff. What is this stuff? And it's the only substituent, so we don't have to worry about any other additional alphabetizing or numbering or anything like that. So on carbon 5, we have this branched substituent. So whenever you have a branched substituent, you have to make sure that that is in parentheses, and that's part of the clue that, oh yeah, it's a branch of a branch. So then we just deal with this part of the name. So it's 1-bromo. So right now what's in parentheses is just the naming and the numbering of the substituent. Dash 2-methyl, the whole thing is 3 carbons, so it's 2-methylpropyl. And then we have the rest of the stuff. In this case, the rest of the stuff is just the parent. And because we don't have another substituent, we don't need the hyphen there. So it's 5, 1-bromo 2-methylpropyl, 10 carbons decane, and there's the name.